SB Engineering, previously known as Hye-dong Bridge, is a leading construction and engineering firm in South Korea renowned for its innovative approaches in bridge building. Among its recent notable projects is the construction of the Yonggyu Bridge, a significant undertaking that utilized the S-bark method, a proprietary technique developed by the company to streamline the process of constructing complex bridge girders. This approach has garnered attention for its unique ability to improve construction efficiency, safety, and structural integrity, especially for large-scale projects like the Yonggyu Bridge. Background on SB Engineering and the S-bark method. SB Engineering has a long-standing history in infrastructure development, with roots tracing back to its establishment as Hye-dong Bridge. Over the years, the company rebranded itself to SB Engineering, reflecting its evolution from a local bridge building firm to a technologically advanced entity in structural engineering. This growth was driven by its commitment to research and development, particularly in creating efficient and robust construction methodologies. The S-bark method is one of SB Engineering's flagship innovations, designed to tackle the challenges associated with constructing large girders for bridge decks. Traditional girder construction methods are often cumbersome and can pose safety risks, as they involve complex staging and heavy equipment to lift and assemble massive concrete or steel segments. The S-bark method addresses these issues by employing an incremental launching technique that allows the girder to be constructed progressively along the span of the bridge, reducing the need for extensive staging and lifting equipment. This method not only saves time, but also minimizes the environmental impact by reducing on-site resource demands and construction footprint. The Yonggyu Bridge is part of a major infrastructure initiative aimed at improving connectivity in the Yonggyu region of South Korea. Situated in a scenic area with significant environmental sensitivities, the project required careful planning and innovative solutions to minimize disruption. The bridge spans a considerable distance, with multiple segments requiring substantial structural support. These requirements made it an ideal candidate for the S-bark method, which facilitated a more streamlined construction process without compromising on safety or durability. The bridge's design includes multiple girders that are essential for supporting the deck and ensuring stability across various spans. Using the S-bark method, SB Engineering was able to construct each girder incrementally. This method proved beneficial not only in terms of time and cost efficiency, but also in preserving the ecological surroundings of the construction site. The S-bark method, as applied in the Yonggyu Bridge, involved a series of well-coordinated stages that allowed for the girder to be constructed piece by piece. The process begins with setting up a series of temporary supports, or staging points, along the bridge's alignment. Unlike traditional methods, where each girder segment is lifted and placed individually, the S-bark approach allows segments to be added sequentially, with the structure essentially growing outward from a central point. Each segment is prefabricated and then moved into place using a specialized launching mechanism. As the bridge lengthens, the supports are repositioned and the structure is further extended. This method reduces the need for large cranes or excessive temporary supports, making it particularly suitable for locations where space is limited or where excessive construction staging would disrupt local ecosystems. Advantages of the S-bark method in Yonggyu Bridge construction. The S-bark method brought several advantages to the construction of the Yonggyu Bridge. First, it enhanced safety by minimizing the need for heavy lifting equipment, which is traditionally associated with greater risk of accidents. The incremental approach reduced the pressure on workers to complete high-stakes maneuvers, as each segment was installed in a controlled, predictable sequence. Second, the method contributed to cost savings. By reducing the dependency on heavy machinery and minimizing temporary supports, the S-bark method cut down on material costs and labor time, making it an economically viable choice for large-scale projects. This efficiency translated into faster project completion, which is a critical factor in infrastructure projects with strict timelines. Proyek Pemasangan Girder PCI, Precast Concrete Girder Sepanjang 45 meter dan 30 meter di Kabupaten Demak, Jawa Tenga, Merupakan Bagian Penting dari Infrastruktur Jembatan yang Membentang di atas Sungai Gumawang. Proses Pemasangan ini melibatkan metode khusus dengan menggunakan launcher untuk mengangkat dan meletakkan girder beton besar yang memiliki berat masing-masing sekitar 100 ton. Metode ini memastikan stabilitas serta keselamatan selama pemasangan girder di area yang memiliki kondisi geografis menantang. Detail teknik pemasangan dengan launcher digunakan sebagai alat utama dalam pengangkatan dan pemasangan girder. Alat ini memungkinkan girder diangkat dari tempat penyimpanannya, kemudian diposisikan secara presisi di atas tumpuan atau pilar jembatan, dengan panjang span keseluruhan mencapai 458 meter. Metode ini sangat efektif karena memungkinkan pemasangan girder dari satu ujung jembatan ke ujung lainnya secara bertahap. Teknik pemasangan menggunakan launcher juga didukung oleh penggunaan troli dan rel, yang memungkinkan launcher bergerak secara longitudinal sepanjang jembatan. Troli dan rel ini memberikan fleksibilitas pada launcher untuk menjangkau setiap bagian dari span, sehingga mempermudah proses pemasangan girder satu persatu secara teratur. Dengan demikian, proses instalasi girder dapat berjalan dengan lebih cepat dan minim risiko karena tidak membutuhkan alat berat tambahan seperti crane besar yang biasanya memiliki keterbatasan akses di lokasi sempit atau berbatasan langsung dengan sungai. Keuntungan metode launcher salah satu keuntungan utama dari metode ini adalah efisiensi waktu dan tenaga kerja. Pemasangan girder dengan launcher lebih cepat dibandingkan metode konvensional, karena launcher dapat mengangkut dan meletakkan girder tanpa harus memindahkan peralatan utama dari satu lokasi ke lokasi lain. Selain itu, launcher yang dilengkapi dengan troli dan rel memudahkan pengaturan girder agar berada dalam posisi yang presisi sesuai perencanaan konstruksi. Keuntungan lainnya adalah aspek keselamatan, karena girder diangkat dan ditempatkan dengan alat khusus yang didesain untuk menahan beban berat hingga 100 ton, risiko kecelakaan kerja berkurang signifikan. Selain itu, penggunaan troli dan rel menambah stabilitas launcher selama proses pemasangan sehingga girder tidak mudah bergeser dari posisi yang diinginkan. Pemasangan girder PCI di atas sungai Gamayang menghadirkan tantangan tersendiri, terutama terkait dengan stabilitas dan keamanan. Sungai ini memerlukan perencanaan yang matang agar pemasangan girder tidak terganggu oleh kondisi air dan aliran sungai. Oleh karena itu, penempatan launcher, rel, dan troli dirancang dengan mempertimbangkan kondisi geografis dan faktor lingkungan sekitar. Selain itu, tim konstruksi harus memastikan bahwa semua peralatan, termasuk launcher, berada dalam kondisi prima, karena beban yang diangkat sangat berat. Pemeriksaan berkala terhadap kekuatan dan stabilitas alat sangatlah penting untuk menghindari risiko kerusakan dan kecelakaan. The Gateway Wa project in Perth, Western Australia, showcased its innovative construction techniques through an impressive time-lapse of the underpass installation in its southern zone. This underpass serves a critical function, linking the principal shared path, PSP network, to allow pedestrians and cyclists to cross Roe Highway safely west of Tonkin Highway. The time-lapse video captures the complexity and efficiency of the entire construction process, compressing months of work into a few minutes of engaging footage. The video begins with bulk excavation, where heavy machinery removes vast quantities of soil to create the underpass trench. This phase of construction is essential for laying the groundwork, both literally and structurally, for the underpass. Once excavation is complete, the project team moves on to the foundation work, which ensures the stability of the structure. This phase includes placing concrete footings and reinforcing steel to bear the load of the underpass and any traffic above. Following the foundation work, the time-lapse reveals the progression to structural assembly. Here, prefabricated sections are placed into the excavated space, demonstrating an efficient approach that minimizes time spent on site and enhances safety for the workers. The video highlights the precision of this operation, as each segment is meticulously aligned to form the tunnel-like structure of the underpass. This prefabrication approach is a key innovation in large infrastructure projects, allowing for both faster installation and higher quality control. As the underpass structure takes shape, the project moves to the asphalting phase. This final layer provides a smooth, durable surface for pedestrians and cyclists, connecting seamlessly to the PSP network. As the video concludes, the transformation from a bare excavation site to a fully functional underpass is evident, showcasing the skill and coordination required for such a large-scale infrastructure project. The Phu My Bridge, completed between 2007 and 2009, is a landmark infrastructure project in Ho Chi Minh City, Vietnam, symbolizing the city's rapid transformation and aspirations to be a major urban hub in Southeast Asia. Spanning the busy Saigon River, this impressive bridge has become a crucial part of the city's Ring Road, a highway encircling Ho Chi Minh City. This road aims to streamline traffic flow from the densely populated Mekong Delta in southern Vietnam to the central and northern parts of the country, addressing Vietnam's urgent need for modern transport networks to support its economic growth. The bridge is notable for being Vietnam's first major privately funded infrastructure project. It was designed and constructed by the international consortium BBHI, consisting of Germany's Bilfinger, Berger Civil, and the Australian company Balderstone Hornibrook. Drawing on their extensive experience in cable-stayed bridge construction, including projects like the Anzac Bridge in Sydney and the Centennial Bridge across the Panama Canal, BBHI completed the Phu My Bridge ahead of schedule and within budget, a remarkable feat in large-scale engineering. Construction on the Phu My Bridge began in February 2007, and it officially opened to traffic in September 2009. Its design features a cable-stayed structure, where the bridge deck is suspended from cables anchored to two towering pylons, which bear the entire load. This design was chosen for both its strength and aesthetic appeal, making the bridge a new icon in Ho Chi Minh City skyline. A unique aspect of the project was the precise and challenging process of deck construction and cable installation. After finishing the deck and cable installations on the District 7 side, a similar setup had to be replicated on the District 2 side. This required transporting massive travelers, special construction platforms, across the river, each taking about a week to move and set up. A process that demanded meticulous planning and flawless execution. The final deck closure was celebrated on May 19, 2009, marking the triumphant completion of the 2.1-kilometer bridge, which now links Districts 7 and 2 for the first time. The Phu My Bridge stands as a testament to Vietnam's growing infrastructure capabilities and its ambition to connect its dynamic cities and regions. Today, it is more than just a bridge. It represents a milestone in Vietnam's development journey, symbolizing connectivity, progress, and an exciting future on the world stage. The operation utilized a powerful 300-ton crane to lift and position each beam precisely. This crane's high lifting capacity ensured safe handling of heavy loads, essential for accuracy and structural integrity. The team successfully lifted and positioned 9 large concrete beams, each requiring careful handling due to their substantial weight and size. Using advanced lifting technology, each beam was securely and precisely moved into place, maintaining strict alignment and safety standards. The lifting operation showcased innovative precision with the use of the Vita Load Navigator, a state-of-the-art, remotely controlled system designed to enhance safety and accuracy. Unlike traditional lifting methods, the Vita Load Navigator allows for precise control over each beam's position without the need for workers to guide the load directly, reducing on-site risk. This tool operates through a remote interface, providing operators with exceptional control, even for high-weight beams, and eliminates sway with the help of high-powered fans. By maintaining stability and accuracy within millimeters, the navigator ensures the beams are securely positioned, minimizing potential hazards and enhancing construction efficiency. Temporary beam guides were used to secure each beam's exact position, enabling precise alignment within 5 millimeters. These guides allowed the beams to be landed accurately without requiring personnel close to the load, significantly enhancing safety. This setup minimized manual adjustments, streamlining the process and reducing on-site risks for workers. The piling process for the Kalimalang Bridge construction is a critical phase in the overall development of the bridge, playing an essential role in ensuring the structural stability and safety of the bridge. Located in the East Jakarta area, the Kalimalang Bridge is a key infrastructure project that connects various regions and facilitates transportation across the Kalimalang River. Given the nature of the location and the varying ground conditions, the piling process becomes a pivotal aspect of the bridge's foundation design. Purpose of piling in bridge construction. Piling is the process of driving or drilling piles into the ground to provide a solid foundation for large structures like bridges. The primary purpose of piling in the Kalimalang Bridge construction is to transfer the load of the bridge to deeper, more stable soil layers when the upper layers are too weak or unstable to support the weight of the bridge and the traffic it will carry. In the case of the Kalimalang Bridge, the soil conditions are such that piling is necessary to provide the strength required for a safe and durable structure. Types of piles used. The Kalimalang Bridge's design necessitates the use of various types of piles based on soil conditions and the specific requirements of each bridge pier. The two most common types of piles used are driven piles and bored piles. Driven piles. These are pre-manufactured piles made of concrete, steel, or wood that are driven into the ground using a pile driver. Driven piles are typically used in areas where the soil is dense enough to allow the piles to be driven to the desired depth without the need for further excavation. Bored piles. In areas where the soil is softer or there are obstacles like rocks or water, bored piles are used. A drilling machine is employed to create a deep hole, which is then filled with reinforced concrete. Bored piles provide better stability in soft or unstable soils, making them an ideal choice for certain sections of the Kalimalang Bridge. The piling process steps. The piling process for the Kalimalang Bridge construction can be broken down into several key stages: site preparation and surveying. Before the piling begins, the site is thoroughly surveyed. Soil testing is conducted to understand the composition and characteristics of the ground. This information helps in determining the appropriate type of pile and the required depth for each pile. The site is cleared of any debris or obstructions to ensure smooth operations. Pile installation. Once the preliminary work is complete, the pile installation begins. For driven piles, large pile drivers are used to hammer the piles into the ground. For bored piles, a drilling rig is used to excavate deep holes into the earth, after which they are filled with concrete and reinforced with steel bars for added strength. Pile testing. After installation, the piles are tested to ensure they can bear the required load. Load tests are performed by applying a predetermined weight to the pile and measuring its deflection. This step is crucial to confirm that the foundation can handle the stresses imposed by the bridge and the traffic. Capping and completion. After the piles are in place and have passed the tests, the top of the piles is capped with a concrete beam to connect them. This capping ensures the piles work together as a cohesive foundation system, providing the necessary stability for the rest of the bridge structure. Challenges in the piling process. The Kalimalang Bridge project faces various challenges related to the piling process. The river's proximity introduces challenges in terms of water table levels, requiring careful planning for foundation stability. In addition, the site's urban nature and surrounding infrastructure can complicate the installation process. Ensuring minimal disruption to the local community and traffic flow is an ongoing consideration.